Welcome to Gateway 4, simplifying radicals today. Now, part of what we're doing today is going to be kind of an extension of Gateways 1. Remember when we were talking about number pairs, and it's nice to be able to be quick with number pairs? We're going to take 50, and we're going to try to come up with a pair of numbers that multiplies to 50. Except we're not interested in all the number pairs. We're not going to go like this, 1 times 50, 2 times 25, although we might. Because actually what we're looking for is we're looking for a factor of 50 which is a perfect square. And what's a perfect square? Well, there's lots of perfect squares. Remember, 1 times 1 is 1. That one's not very interesting. But like 2 times 2 is 4. 4 is a perfect square. 3 times 3 is 9. 9 is a perfect square. 4 times 4 is 16. 16 is a perfect square. 5 times 5 is 25. Another one. 6 times 6 is 36. There's another one. 7 times 7 is 49. There's another one. 8 times 8 is 64. There's another one. 9 times 9 is 81. There's another one. Let's do one more. 10 times 10 is 100. We don't even usually have to go that high, honestly, but hopefully not higher than that. But anyway, these numbers, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Hopefully those numbers are, very familiar to you. If you know your times tables, those would be the numbers that are on the diagonal, right? Because if you looked up a 3 times a 3, then on the, well, I didn't line up the diagonal very well, but on the diagonal for 3 times 3, you'd find a 9 and so on. So these numbers are front and center when you're trying to simplify something like that. Okay. So again, the question is, does 50 contain any one of these factors? And it does. Hopefully you're seeing that it has a 25 in it. So here's how we proceed. We go like this. Maybe I'll do a different color to try to keep this a little clear. So instead of radical 50, we say, oh, the 50's got a 25 in it. So you can, I don't usually write this, but you can think this instead of writing it if you want. So it's like 50 is a 25 times a 2. Now this works. You can break root 50 as a root 25 times a root 2. It works. And if you don't believe me, try it on your calculator someday. It works. Just as an aside, please never do this. If you had like a 25 plus a 16, you could not break it up this way. No, it does not work for addition. Because a 25, root 25 is 5, root 16 is 4, so we're getting a 9. But 25 and 16 is 41. Is the root of 41 equal to 5 plus 4? No, it is not. It does not work for addition, but it does work for multiplication. And because it does work for multiplication, it gives us a nice method for simplifying our radical. Because radical 25, the root of 25, we know what that is. It's 5. And that's what's multiplying the square root of 2, or radical 2. 5 radical 2. The square root of 50 is 5 radical 2. Now when it comes to x's, careful here, you're not going to take the square root of the 16. The 16 is different. The 16 is an exponent. What you're going to do instead is actually, the shortcut, just cut the 16 in half. This is x to the 8th. So divide the exponent by 2. Come on, you're an eraser. Okay, you're still an eraser. Cool. Okay, so cut exponent in half is what I want to say here. For a square root, you would cut the exponent in half. Half of 16 is 8. The answer is x to the 8th. I can prove it to you. Remember, the idea of a square root is what times itself equals the thing inside. What times itself equals x to the 16th. I'm saying the answer is x to the 8th. Is that true? If I multiply x to the 8th times itself, do I get x to the 16th? And of course you do. Remember that law about adding your exponents together? 8 plus 8 is 16. It works. It works great. So when you're playing with numbers like this, you need to factor out a square rootable factor, a perfect square factor. Look for something. Look for either a 4, a 9, a 16, a 25, a 36, a 49, or whatever. When it comes to x to a power, though, it's a completely different ball game. You just cut the exponent in half. That's all you do. You don't take the square root of this 16. No, you don't. You just cut it in half. So you got to remember those two basic rules for simplifying square roots. Now, these next two examples, you have to use both of the rules. So let's do that. So you have to look at the 45 and you have to look at the x cubed both separately. So the 45, what's it got in it? I'm going to look back up at this list here and I'm going to say, oh, it's got a 9 in it, right? 45's got a 9 in it. So I can think of this as the square root of 9 times a 5. Now as far as the x cubed goes, you can't really cut 3 in half, not evenly, but you can cut 2 in half. So what you do is you split that x cubed up as an x squared times an x. Again, this is something you can cut in half, or that exponent is something you can cut in half. That means the square root of x squared is something that you can find. And 9 is something you can square root. So basically, you take the square root of 9 and you get a 3. That stays inside. You take the square root of x squared and you get an x. That stays inside. So let's put the insides back together here. See where all these pieces are going? So I was able to take the square root of 9. That got me to there. I was able to take the square root of x squared. That got me to there. And then the 5 and the x are still stuck inside. They're stuck in there forever. Now actually there's something very important here that I need to mention. So maybe I'll use like a reddish. There we go. Hey. This answer is not quite right. It's not quite right. You would not get this right if you left it that way. The thing is, this symbol always represents a positive quantity. If you just see this radical symbol, it represents a positive quantity. In other words, if I say, hey, what's radical 16? You get 4. That's a little different. If you're thinking of square roots of 16, you might say, well, 16's got 2 square roots, doesn't it? And it does. But that's not what this symbol is. This symbol is the principal root symbol. The principal root symbol. And guess what? The principal root is positive. So radical 16 like this, that's supposed to be a 16, is just positive 4. It is not plus or minus 4. Now, if you were solving equations, like if you had something like this, x squared is 16, the way you would solve it is you'd say take the square root of both sides. And then you would have to put a plus or minus in front. Do you remember doing this at some point in your life here? You would have to put the plus or minus in front. Why do you have to put the plus or minus in front? Because the radical 16 is a 4. And what you mean is either plus or minus 4 are both solutions to this equation. So when we're taking the square root, we have to put that plus or minus there. Because if we didn't, radical 16 is not plus or minus 4. It's just plus 4. Okay, that's what I'm trying to say here. This symbol represents a positive quantity only. Radical 16 is not plus or minus 4. Radical 16 is always positive. So let me get this stuff out of the way. It's kind of getting in the way, isn't it? Yep. So how do we fix our answer then? Because, you know, if x was a negative number, this would not be a positive quantity. Well, here's the easiest way to fix it. Put the x in an absolute value. There we go. All done. So this is our answer. So a lot of people don't really know about this whole absolute value thing, but it is crucial. You could not say that this was the answer, unless you said something like assuming x is positive or something. If you assume x is positive, it's okay, because then x is positive and the whole thing's positive. But if you don't assume x is positive, then you have to put these absolute value bars there, okay? Please remember that. I'm pretty sure these are going to be the only 2 examples where this comes up. So to make sure your answer is positive, because again, this symbol means positive. So to make sure your answer is positive, if you've got an x out here, put it in absolute value bars. What do you say we change colors and go to the next one? All right, we got a 28, we got an x to the 5th. So the 28, what you do is you look for a perfect square. And, you know, here's our list again. You're looking at this whole list here. Yes, I am. I'm looking at that whole list there. And really the 4 is what we're going to use there. So the 28 has a 4 in it, so let me put the 4 there. And let me put 4 times 7. Now the x to the 5th. Remember, with exponents, you're just going to cut the exponent in half. But of course, you want to cut an even number in half. You don't want to cut an odd number in half. So x to the 5th, well, you have to think of that as x to the 4th times another x. That way you've got an even exponent here. Okay, now we can go ahead and start taking some square roots. So theoretically, that's all inside the square root. You can rearrange this if you want, if you like this look better. Put the 4 and the x to the 4th over here, put the 7 and the x over here, right? You can multiply in any order, so I'm just mixing the stuff up. The idea is both the 4 and the x to the 4th, I can just go right ahead and take the square roots. Square root of 4 is 2. Square root of x to the 4th, just cut the exponent in half, it's x squared. And then don't forget, you still got this root, or radical 7x over here. Now actually, I don't need the absolute value bars. Why? Well, this does have to be a positive quantity, but look, x squared is going to be a positive quantity, so actually we didn't even need it there. We got lucky. So maybe that's the only place we actually need the absolute value bars is on this example. Well, we'll see if it ever comes up again. But geez, do keep that in mind. If the radical symbol indicates a positive quantity, so don't put something down that might be negative, because then half the time you'll be wrong. So what do we got on the next page? Oh, we got cube roots. That little 3 there says cube roots. Okay, so now we got to be thinking in terms not of finding a perfect square, but of finding a perfect cube. So things like, what's 2 times 2 times 2? That's what you mean by cubing. Times itself 3 times. 2 times 2 times 2 is 8. That's a perfect cubed. What's another one? Well, if you go 3 times 3 times 3, 3 times 3 is 9, times 3 again is 27. There's a perfect cube. Let's just make like 2 more. We don't usually go too high on these. But like if you did do a 4 times a 4 times a 4, what would you get? Well, 4 times 4 is 16, and 16 times 4, which is the same as double it twice, you get 64. That's a cool number, huh? You could take the square root of 64 and get 8, or you can take the cube root of 64 and get 4. Either way. And maybe one more. 5 times 5 times 5 comes out to 125. And of course the list goes forever. You can always generate as many of these as you want. But looking at this here, 24, the question is, can I find a number pairs, a pair of numbers, where one of the numbers is one of these? Well, it's certainly not going to be a 27, right? But the 8 works. So you break this up. You think of this as a cube root of 8 multiplying a cube root of 3. That works. It works for multiplication. Now the reason you're doing this is so that you can make it look a little nicer. The cube root of 8 looks nicer. It's a 2. And then the cube root of 3, well, you're stuck with it. And there's your answer right there. So let me get that out of the way. So the cube root of 8 is just 2. That's the simplifying we're able to do. The cube root of 3 we cannot simplify, so we just leave it. So instead of cube root of 24, this would be called the simplified radical form because, well, it's a little simpler. Now, over here with exponents, I wonder if you're anticipating this. Just like we were saying for square roots, right? When you have an exponent, you're not taking the square root of the exponent. Well, when you have a cube root, you're not taking the cube root of the exponent either. Okay, what you're doing, in the case of the square root, we divided it by 2. In the case of a cube root, we divide the exponent by 3. And I'll show you that this works. So 27 divided by 3 is what? 9. So I'm trying to say, oh, that looks messy. I'm trying to say that the cube root of x to the 27th is x to the 9th. Am I right? Well, I'll show you. So remember, a cube root means something like this. You multiply it by itself 3 times. So we're saying, you know, what times itself 3 times is going to give us x to the 27th. Well, if you go x to the 9th times itself 3 times, what would you get? Remember, you would add your exponents together. That's one of our laws of exponents. 9 plus 9 is 18, plus 9 more is 27. It works, right? Because you add the exponents, so it works. So if you're taking a root then, a cube root, you're dividing your exponent by 3 for a cube root. got some combo moves down here. So, you've got a 40, you've got an x to the 5th, and you got to remember that you're playing sort of like two sets of rules, one for each. So let's see now here. With the 40, we want to be trying to find a cube rootable factor. We want to break the 40 up into a pair of numbers where one of them is one of these cubed things. And actually the 8 works again. There's an 8 in that 40 there. Let me go to blue. So the 40 has an 8 in it. Cool. So split up the 40 as an 8 times a 5. Cool. X to the 5th. We want to divide the exponent by 3. That means we want to do things like x to the 3, x to the 6, x to the 9, these are all the cube rootables, right? Because you can divide their exponents by 3 and it comes out even. Well, 5 doesn't work. But the closest you can get to 5 on this list is here, right? So you can split this up as the cube root of x cubed, and x to the 5th would be what you get when you take x cubed times an x squared. Okay, so I split it up into 4 cube roots. You could, rearrange this if you're more comfortable. This is something cube rootable. This is something cube rootable. So I'll put those next to each other. And then these are going to be leftovers. The 5 is going to be a leftover. The x squared is going to be a leftover. I'll put those over here, and that's a 3. Now it's time to actually take the cube root. The cube root of 8 is 2. The cube root of x cubed is x. And then these are leftovers. That's just going to stay the way it is. And so there's how you simplify that one. Do I have to worry about this absolute value type stuff? Not with a cube root. The cube root of a negative is negative. So if it's negative, it's negative. We don't care. It's going to work. It's going to be fine. That's only something you worry about for square roots and fourth roots and stuff like that. Any even root. So this one, over here. Back to blue. Play with the 54, play with the x to the 10th separately. So with the 54, we're looking for a perfect cubed. Does 8 go into 54? Nope. What's the next perfect cube? 27. That's what a 3 by 3 by 3 is. Does 27 go into 54? It does. 54 is 27 times 2. Maybe I'll just write it this way this time. X to the 10th. Now in this case, you want to take the 10 and divide it by 3. You can't really divide 10 by 3 evenly. The closest is a 9. You can divide 9 by 3. So you split the x to the 10th up like this. So the cube root of 27 is just a 3 that comes out to the front. The cube root of x to the 9th, I would cut my exponent, divide it by 3, and so that becomes an x cubed out to the front. You can't do anything with these. They're stuck inside of the cube root tent forever. So you just kind of put them there. And that's how you simplify that one. Okay, what do we got on this page? One more page. Oh, these things. These are denominators. So you might look at square root of 3 and say, I can't simplify that. And it's like, yeah, you can't. But this is not simplified radical form because we don't like radicals in the denominator. We just don't like it. If there's a radical in your denominator, it's not considered simplified radical form. So the standard trick for this kind of thing, you'll like this. I got a square root of 3 and I don't like it. Well, remember you could change fractions, this way. Multiply the top and bottom by the same thing. Multiplying by root 3 over root 3 works great because up here, 1 times root 3 is, well, that's root 3. And on the bottom, root 3 times root 3, well, it's going to be just a 3. And if you need to think about that, think about it this way. What is root 3 times root 3? It's the same thing as root 9, right? 3 times 3 is 9. And root 9 is 3. So this is just a shortcut you can take whenever you have a square root repeating itself like this. Root 3 times root 3 is just 3. Cool. Do I want to do this one next? I think I'll do this one down here next. It looks more complicated, but it actually isn't because, well, here's the thing you want to realize. You got a fraction, right? It looks like I have a fraction inside of a radical. But in the same way that you can break up, if you had multiplying, you can break it up. Well, dividing, you can break up too. So in other words, you can look at this way. A square root of 25 on the top, a square root of 18 on the bottom. First, let's simplify those. Square root of 25, that one simplifies really nice. Square root of 18, well, we got to work a little bit. Remember, that's got a 9 in it. 18 is 9 times 2. So I could take the square root of 9 to get a 3, and then the 2, I cannot take the square root, so it's stuck in the square root. And then you say, well, that's better, but I still got to get rid of that radical 2 because we don't like radical 2's in the denominator. So you multiply top and bottom by radical 2, and you get, for an answer, up here, 5 times radical 2 is what it is. And on the bottom, well, let's see now here. You'd have, what is this? This is 3 radical 2 times radical 2. Well, you know that the radical 2 times a radical 2 is just a 2, right? Radical 2 times radical 2 is radical 4, and radical 4 is 2. It's just a 2. Just don't forget the 3 there. So you get 3 times 2, you get a 6, like that. Okay. So if you have a fraction inside of a radical, that doesn't count as simplified radical form either. Just take the square root of the top and bottom separately and keep going until you get to a form like this. A radical on top, we don't mind. A radical in the denominator, we do mind. A fraction in a radical, we do mind. All right, so why did I save this one for last? Because of that cube root, that's why. Now, it'd be great if you remember this for the rest of your life. Here's the thing. Over here, let me use a different color, like maybe, I'll just use gray. So why did it work here? Let me erase the green if I can. Okay, why did it work over here? Let me erase the green if I can. Why did it work over here to multiply square root of 3 times square root of 3 to get a 3? It worked because, back to gray, if another way to write this is to say it's the square root of 3 squared. The square root is canceling the square. Get it? So when you have a square root, what you're trying to do is build a square inside. The 3 times a 3 gives you a 9, which is a perfect square. That's what enables you to simplify this. So over here, if you're thinking we're going to multiply by, let's just look at the 3 part for now. Well, cube root of 3 times cube root of 3 is cube root of 9, and that doesn't simplify at all. That doesn't help you at all. So no, we're not going to just copy like we did over for the square roots. You got to do this a little more carefully. So let's go back to blue. Since it's a cube root radical, you want to build the insides up to cubes. The cube root of cubes will cancel. But since it's a cube root, we need to build up to cubes. What have I got there? I've got a 3 to the 1 power. Well, I'm going to have to multiply by 3 to the 2 power in order to get 3 to the 3 power. Get it? Now the x squared, that's close to 3 power, so I'll have to multiply by the cube root of x. X squared times x gives me an x cubed. So here's the action. On the top, whoops, yeah, let's do this. On the top, I've got the cube root of these two things times 1. So on the top, I've got the cube root of, I might as well call it 3 squared of 9, and that's an x. Okay, both under the cube root. That's a 9 and an x under the cube root. On the bottom, I've got cube root of all this stuff multiplied together. I got a 3 times a 3 squared makes a 3 cubed. And I've also got an x squared times an x makes an x cubed. And that's what I meant by build up to cubes. Build the insides up to cubes, because that's what makes the next step possible. The next step is that that cube root on the bottom goes away, because the cube root of 3 cubed, that's 3, and the cube root of x cubed, that's x, and here's your answer here. Okay, so of course we're going to be going over this in class. I think we will have already been doing this in class by the time I hand out the practice gateways, but make sure, hey, it's one of your quiz questions. Make sure you follow this idea. Again, if it's a square root, it's nice. You want to make a square, so you just make a copy of it, and you've got a square. Anything times itself, you got a square. But for cube roots, you need to build up to cubes, which means you're not going to be just, I didn't just multiply by 3x squared. This is a 3x squared. I did not multiply by the cube root of 3x squared. I actually have a 3 squared and an x to the 1 power. It's kind of the opposite of what you might have expected. Okay, so again, build up to cubes. Okay, so I think that's all of it, right? Yep, that's all of it. Cool.